All right, I think we're working now. I think we're working. Yeah, things are much better at my end now. Had a lovely computer crash, so that was fun. So I'll give it a little bit. We'll see how this goes, because obviously it is annoying that that happened. Such a rookie setup. That's what it is, causing a crash. Oh, I need to stop knocking that as well. It's amateur hour. Okay, right. I knew we had electricity last time, but at least I thought I'm testing that everything works now after the crash. So that's beautiful. Right. Okay, electricity. Okay, is there any particular thing in electricity or just all of it? I mean, all of it might be a little bit tricky, but if there is anything in particular, obviously, I can start with that. Okay. Right. So electricity kind of has a few kind of aspects to it, really, that you need to be happy with. The first one is circuits. Okay, actually, what they are. Okay, that includes things like your kind of like basic units, what they mean, how they relate to actual electricity. You've got required practicals. Now, mostly you've got the resistance in the wire. That's the big one. You've got like electricity, like so domestic electricity, like electricity in the home. Okay, and obviously, as always in this paper, there's a hearty amount of equations. So the first thing I'm supposed to think is what actually is electricity, because we often kind of overlook that. So electricity is it's quite simple, really. Okay, it is a charge. Now, most often that's a negative charge because of the electrons. Okay, moving in a circuit. Okay, so fundamentally, for an electrical circuit, you need to have some form of charge and a closed loop. If you don't have a closed loop, you're not going to have an electrical circuit. Unit conversions. Is there any unit conversions in particular that you find tricky, or is it just like the milliamps and all of like kilowatts and stuff like that? Okay. Now there are kind of 3 to 4 main units with electricity. First one we need to be happy with is current. Now, current is our flow of charge. And all of these were discovered by old 1700s white men, so they named them after themselves, obviously. So current is our flow of charge. That was named by Mr. Ampere, so that is the amp. Okay. You then have potential difference. Now, potential difference is quite a weird one because Multiply, divide. Okay, yeah, we'll do some equation practice, because I think, like, if you can smash an equation question on this, you're going to get like half marks. So you have potential difference. Now that's also called the voltage, and your teacher will often call it that, which gives away what it is. Now I like to think about this as kind of, it's the energy per charge. But in normal words, what do I think of that as? I think of that as kind of the push, how much oomph it's got as it goes around the circuit. And this is measured in volts. Okay, you have resistance. Resistance is how much you oppose the flow. So that's kind of the opposition to the current. And again, this was discovered by Mr. Ohm. Okay, that has a funky symbol that looks like that. Okay. So we've got our basic unit. So this is probably quite a good idea to start to introduce the equations. Now remember, you do not need to remember the equations, but it is a bit weird because the unit of this is A for amps, but in equations it's given the letter I. Okay, this one's easy because it's V and V. And resistance in equations is R, and then it has that weird symbol for the unit. Okay, so first thing is just make sure you use the equation sheet. You'll know that in lessons to death, I talk about FIFA. Okay. And the reason I talk about FIFA is not the corruption ahead of the World Cup, but instead, okay, because if we follow it, we will get as many marks as we possibly can on these equation questions. So we formula, we insert, we fix, and then we get the answer. So when you're talking about if you should multiply or divide, that really is this stage, the fix. Okay, so I'll tell you what, I've got a few past papers near me here. So here's a simple one. Here's a simple one. Okay, it says here, a student connects a resistor to a cell for 60 seconds. The current through the resistor is 0.97 amps. Calculate the charge flow. Now again, it'll either be given to you or is in the equation sheet. So you've got it there. Now, even though it's there, I'm going to write it again because I want to follow that idea of FIFA. So Q equals IT, is it in symbols, weirdly? Okay, so that's my formula done. Tick. I'm then going to stick the numbers in. I don't care about units at this point. I'm just going to stick numbers in. Okay, so Q is what we're trying to work out. That's the charge. No idea what that is. I is 0.97. Time is 60. Okay, now here just so happens that that's in seconds, which is fine, and that's in amps, which is fine. So we're kind of doubly okay. Everything here works out as a time, so I don't need to do any fixing or anything like that. This is as straightforward as it gets. Okay, no such thing as an old calculator science paper. Stick that in, and that would be, off the top of my head. It's like 67.2, something like that. Okay, and then C for coulombs. Okay, so that is our first bit. So that in a normal equation, this so far you'd get a mark for sticking it in, and you get a mark for the answer. You'll notice this is 3 marks. That means there's 3 things to do. Stick it in, answer. The third thing is for remembering that to 2 significant figures. So this to 2 significant figures will, great. 6, 7, great. I hate myself a little bit. Okay, and that'll be our 3 marks. Okay. Now, let me locate you a harder one where I show you how to think about it more with the rearrangement. That still wants the energy, so that's still fine. Here we go. Right, here's an absolute classic. Lovely. Right. So it says here, the potential difference across a piece of wire is 2.1 volts. The current in the wire is 0.3 amps. Calculate the resistance of the wire, write any equation you use. So again, we go straight to our equation sheet. Bosh. That's what it is, V equals I times R. Now, that's our F formula. So I am still going to stick with what we've said. I'm going to stick my numbers in. Right, now this is our voltage, so this is going to replace the letter V, so that's 2.1. This is our current, so that's going to replace the letter I, 0.3, and then R we still don't know. That in itself would be 1 mark. This is why I encourage you to do this. Okay, now this is where you go, you're not sure whether to multiply or divide. This now basically now becomes a maths question. All right, so you know you get used to in maths having 6 equals 3x, find x, and you go, right, well I need to divide both sides by 3, and you would probably be even thinking about it like that. Okay, so this is exactly the same. 2.1 equals 0.3 times R. So let's divide both sides by 0.3. And look, I don't even worry about if it's times or divide because I've worked it out just by doing my maths. Again, stick that into a calculator, and the answer is 7 ohms, and that is going to be there. Okay, so this kind of bit here is where I'm referring to as the fixed stage. Now, the other thing that it could do is ask about a unit conversion. Now, that unit conversion is a bit more prevalent on the higher tier, but obviously it does come up on the foundation. Let me locate a nice one for you. There's obviously also double equations and stuff on the higher, where you have to use 2 equations. It's a bit annoying. Camel. Maybe this one's got a beauty. Right, let me adjust this one. So we're gonna get a little bit of a pretend here. Okay, so this one is one about specific latent heat. I know it's not electricity, but we're talking about equations. Now here it's already converted. Okay, it says it's 0.0072 kilograms. But let's imagine that it didn't say that in the question. It said 7.2 grams. Okay, we're still gonna follow FIFA. Okay, write the equation. On the equation sheet, you'll find that energy is the mass times the specific latent heat, E equals ml. I look and see which numbers have I got in the question. Well, I've got energy. Okay, so I'm going to replace the E with that. Okay, M. Well, let's not worry about a conversion yet. Let's just stick our number in. That's 7.2 grams. But on the back of my head, I'm thinking, well, that's not kilograms, so I'm going to need to do something there. And then L, I don't know. All right, that again would be a mark. Okay, so now we enter our fixed stage. Now, this is 2 things to do in this fixed stage. First of all is to sort the units out. Okay, now I know I'm covering it up there, but 7.2 grams, we've got to put that into kilograms. That means I've got to divide by 1,000. So that becomes 0.0072 times L. Now I've got to remember our kind of algebraic principles. I've got 0.00272 times L. Divide both sides by that. I'll get L on its own. Now you'd get a mark for the conversion, and then you'd get a mark just for seeing that working out. Now I stick it into a calculator, and that's going to get my answer. Okay, that one I'm not going to be able to do. I might be able to do it in my head. What's that? I think. Okay. Does that answer your how we work through equation questions kind of dilemmas? Okay. Right. Is there any aspects of the electricity which you'd like me to go through? I know I kind of went off straight away on units and then start to talk about equation questions. But is there a particular aspect of electricity that anyone really wants? Otherwise, I will just ramble. It's not going to be a massive one tonight, but it's at least something and somewhere for you to vent any issues and see what I can do to help. Okay. Right, I'll tell you what, let's do some random electricity stuff in here, shall we? And that provides a nice little catalyst for how we're doing stuff. Okay, so let's take it back to the basics, and the absolute basics are our circuit symbols. Really good source of a lovely tick box question. Right, which one is a variable resistor? Now, I think that the circuit symbols are quite logical. So this is the symbol for a resistor. Okay, now if I put a little dial on it, so this is technically a combined science foundation paper, but it appears on literally everything. It's unlikely that they'll do a tick box on the higher. It would be draw the symbol. Okay, I try and go through fundamentals, if I'm honest, which apply to everything. If I take my resistor and I say, look, do you know what? I want to be able to dial it up or down. That then becomes a variable resistor. Right? Can you see I've just altered the resistor symbol? All right. Now, let's say I want the resistor to be affected by light. Well, I circle it, stick some light on it, and that now is our LDR, which is our light dependent resistor. And let's say I want to adjust it with temperature. Well, it turns out this line is how the resistance changes with temperature. Weirdly, it's kind of the inverse. It's all a bit odd. But that is our thermistor. Okay, so they're all variations of our resistor symbol. Okay, because that's fundamentally what they all are. So which one is a variable resistor? I take my resistor symbol, whack a dial on it, that makes it A. Which one is a thermistor? That's C. So again, in higher, it tends to be, it'll be a box and say, can you draw that symbol for a thermistor? And then you go, yes, lovely. Give me the marks. Thank you. Which component will the resistance decrease when the temperature increases? Okay, that is C, because this is quite weird when you think about it, right? Because what is resistance? Resistance is, this is all of them. The tick box questions will be a foundation, but the symbols appear on literally everything. It's not a higher or foundation only thing. So resistance. Resistance is anything opposing the flow, okay, of the current. So ordinarily, I mean, in class, I've always talked about it like, I don't know if you've ever seen the gauntlet in Gladiators, right? So the gauntlet in Gladiators, they have a big old, like, kind of looks like a half pipe with the mean old gladiators like stood in there, and then they have the person there ready to run through. Okay, well, this is like our charge, this is like our wire, and these are the ions in the wire. Okay, now I want you to imagine that I said, right, you've got to run through, you've got to beat these people. How would you do that? How can you make it easier? Well, the first thing I could do is I can make this really wide, so I've got lots of space to run through. Okay, so if I make it wider, that's easier. Okay, If I, instead of having to go through that, I make it really short, okay, that's easier. Okay, if I swap the big strong gladiators out for a little tiny year 7, okay, that's easier. So that is changing the material. So I want to put a more conductive material. And the other thing is, if I like cool it down, okay, I'll say, right, chill, right, do some breathing exercises, yeah, do some mindfulness, right, whatever, okay, and then they're all like chill, okay. If I make it cooler, all of those things end up with a lower resistance. Okay, so if I have a short wire, smaller resistance. If I have a thick wire, lower resistance. If I make it have a more conductive material, lower resistance. If I have the wire be cold, lower resistance. So most things, if the temperature goes higher, the resistance goes higher. The only thing which really doesn't do that, and this is why this is weird, look, will the resistance, in which component will the resistance decrease when the temperature increases? This is kind of opposite. And that is why the thermistor is its own weird thing, okay? Because the thermistor is opposite to what you usually expect. Now, why have I gone off on this tangent? That's because this comes up when you are looking at IV characteristics, right? So you have to know certain devices. So the first one here, right, where you have a nice straight line, this is the IV characteristics of an ohmic resistor. Something which follows Ohm's law. It is directly proportional. Why and how do I know that? Because it's a straight line and it's through the origin. That makes it directly proportional. Okay. The next weird thing you have to be familiar with, and if I did it backwards, it would do like that, okay, is this shape, okay? Now this is a filament bulb. Okay, now how do I remember this? To me, that kind of looks like a curly F, F for filament bulb. Okay, now why does it do this curve? Okay, why does it do this curve? Well, up here, okay, the bulb is getting hotter. And if the bulb is getting hotter, we've just said over here, if the temperature increases, the resistance increases. So that means that it kind of flattens out to follow that trend. And the other one that you need to be happy with, okay, is this one, okay, where the resistance, that you basically have nothing, 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 way, right? And this is a diode. Okay, now diodes only let electricity go through in one direction, which is why it's flat in the negative direction. You get this what's called a lag period, and then okay. So this is a diode. That thing, okay, only lets electricity through that way. Right, going back to this, in which component will the resistance decrease when the light intensity increases? That is the hallmark of this bad boy, the light-dependent resistor. Okay. Again, always feel free to interject with any questions, any queries, any quibbles, because you don't need to let my ADHD go wild. Right. We have got different arrangements of resistors. It says 2 of the arrangements are in series and 2 are in parallel. Describe the difference between a series and parallel. Right. So series circuits are ones where the components are in the same loop. Okay, and in parallel, they are in different loops. How can you remember this? in series, like if you watch a series on TV, they come one after the other. Okay, and also in parallel, you get parallel lines. Okay, now what does that mean for our circuit? Well, if everything's in the same loop, let's think about a river, right? If there's no offshoot to the river, all the water has to go through every part of the river. So that means that the current is the same everywhere in a series circuit. So there's nowhere else for the water to go. But just like if you've ever been like to the gym or something, or in PE, right, and then they say, right, it's our last exercise, and then they lie to you, and you've got one more, and you're like, I just gave all my effort to that last exercise. You conned me. I've got nothing left. Like Ian Beale. Okay. That means that you have to kind of the electricity kind of knows that in a way, and doesn't give all of its energy to the first thing. So that means that the voltage, the potential difference, is shared between components. Now, for a parallel circuit, it's back the opposite. Okay, so the current is shared, the flow is shared, because I've now got different kind of different paths, and the voltage is the same everywhere. Okay. So, in that foundation, it might be something as simple as components are in one loop in series, like this question. Components are in one loop in series. They have their own loops in parallel. For something like a higher tier, it might start to be thinking about, okay, what's going on with the current, what's going on with the voltage. Now, I know that I've got questions coming up with this, but let's look at this. Let's see what's going on. Here, I've got a 10 ohm resistor, and then another 10 ohm resistor. Okay, so if I if I go outside and I face 10 people in my way, and then I face another 10 people in my way, funnily enough, in series, okay, the resistances add. So here I'd face 20 ohm total of resistance. At foundation tier, that is all the calculations to do with it that you will need. Okay. Next one, okay, here I've got 5 in series, 5. That means that it would face 10 ohms in total. Now, resistors in parallel are bizarre, okay? Because think about it like this, right? I've got options now, right? I could go here, or I could go here, right? So imagine I've got a queue of people. Right? Because I've now got 2 paths, I can almost have 2 going at once. So it actually means that they get through this much quicker. So weirdly, when you have resistors in parallel, the resistance actually decreases. That's quite weird. You're adding a resistor, but it actually overall reduces the resistance. Okay? It's kind of like turning a single track road into a dual carriageway. You've now got 2 paths for you to go down. That overall actually makes it easier to flow. So there is a way of working this. This would actually be 5 ohms, but the whole idea is this would be less than 10 ohms and this would be less than 5 ohms. Okay, so it says which arrangement has a resistance of 10? That's going to be R. Okay, which arrangement has the highest resistance? That'd be P. Okay. Right, I'm glad that I turned over this, because this is another like real gimme section, and it doesn't matter what tier it is. This is like, we've got to think about what can we go into the exam just knowing off our heads, and that is domestic electricity. Okay, there are 3 wires in the UK plug. God bless it. Okay, moment of pride for the British plug. Okay, yeah, you don't need to stick your hand up. Just say it. It's all right. Or you're just saying hello. Who knows? You are the Roblox king. Maybe you've got, what's it, garden grow? Is that the one? Who knows? Right, you got 3 here. Okay, 3 wires. Okay. You've got the live wire, and that is brown. PR, brown goes to the right. The neutral wire, BL, blue goes to the left. And up above here, the green and yellow, okay, that is our earth wire. Ah, you know what it is, green and yellow, green and yellow. Okay. Right, how to remember it. Live wire, this is one with all the electricity. If you touch it, your trousers will go brown, okay? It's quite weird because people think of like earth as blue, but maybe you think all like brown because of the dirt. But let's imagine we've got a nice, lovely image of the earth where it's got green on it, okay? So our lovely green earth, okay? And a neutral blue sky. Lovely, calm, scenic, okay? Now, what do they do? So this is what kind of provides the AC potential difference, or alternating potential difference, because that doesn't really make sense saying the alternating current potential difference, is it? Okay, so this here provides the alternating potential difference, right? This is what's given us the oomph. Now in the UK supply, that is at 230 volts. How can you remember that? Because if you touch the wire, it will hurt your teeth. The electrocution will hurt your teeth. 230. 230. Yeah. The neutral wire provides a return path. Okay, so you've gone into the component, you've used it, comes back, right? Remember it's alternating, so it's switching back and forwards, but you can think about a return path. Now, weirdly, this is actually at 0 volts. Like, it should be at 0 volts. When things are connected in, it will become 230 volts. But if I just looked at it, it would be at 0 volts. And that is maintained all the way back at the substation, okay, at the step-down transformer. The earth wire should ordinarily not be used, okay? This is purely there for safety, okay? That's why the British electrical system is good, because we mandate that it's used, unlike Freedom Land, where they do kind of now, but they didn't for a while, okay? Now, that is there only for safety. So it's at 0 volts, okay, and it provides a return path should something become electrically dangerous on the appliance. Okay, it provides a return path to ground. Okay, in some cases, literally a stick in the ground. Okay, and that prevents the electricity going to ground via you and your heart. So let's look at this question. What is the wire? It is the earth wire. What does it do? Okay, it can prevent an electric shock from the toaster because it's providing a much nicer path to ground rather than through you and through your heart. When it is plugged into the main supply, the potential difference between both of those would be 230 volts. Okay, 230. Mains electricity is an alternating supply. Okay, now, so that means it's going like that. Now, this is the other domestic UK supply fact that you need to know, which is how quickly it's alternating. What's its frequency? And the frequency of the supply is 50 hertz. Okay, that means it's going changing direction, technically 100 times a second. Okay, but it's kind of going forwards, back, forwards again, 50 times a second. Okay, like the AQA or something. Okay. The direct supply just maintains a constant flow. Okay, direct supply is kind of like the DC is I'd say more logical when you think about it with electricity. Okay, because you're just doing it. Okay, whereas the alternating is changing direction, and that can seem counterintuitive. But again, if you think about it, like if I had a bit of rope in my hands, if you were holding a bit of rope in your hands, and I shuffled it backwards and forwards, you'd still kind of feel that friction both ways, and I'm transferring energy to you. So, what are the main differences here? Well, if I look at this, first of all, we're changing direction. Okay, so we have positive and negative supply. So we have positive and negative. Okay, you'll notice that also at these bits here, right, technically it's at 0. So there's periods where it's actually at 0. Okay, and the other thing is the peak of the supply is actually higher on this graph than these ones. Okay, so you have higher peaks and lower troughs because it all kind of balances out. Right, the national grid. Let's use that as an opportunity to revise the national grid. Okay, so here is our power station. Okay, we're in Suffolk, so it's going to be our Sizewell C. Look at it, beautiful. Okay, love a bit of nuclear. Okay, spend that important time doing that. Oh, lovely. Beautiful. Okay, and that produces our electricity. Now, in an ideal world, I could just go power station to home. Okay, but I'd have to live close to the power station, and that's what they used to do. The problem you've got is here, you're going to lose electricity. You're going to lose energy. And when I say lose, that means waste, right? You're going to waste energy. Why? Because it's quite inefficient. So what we do is we do this whole palaver. That's not what we do. The power station goes to a step-up transformer. Okay, and what that does is that will increase the voltage. But what that does is it decreases the current. And that means that the electricity in that wire, okay, because it's at a high voltage and a low current, that means that it doesn't get as hot. Okay, and if it doesn't get as hot, it means you're not wasting as much energy. Right, when you charge your phone, right, it feels hot, doesn't it? Right. So by doing it kind of, in this way, you're kind of not you're not making it get as hot. You're not wasting that energy. And the beauty of this is because I'm not wasting as much energy, I can send this across the whole country. Right. I can send this wherever I want. There's my lovely pylons. Right, there they are. Beautiful. Okay, and then the problem is this is now, say, 132,000 volts or 400,000 volts. If I now start to do that into my home, problem, okay, I'm going to start electrocuting myself. It's going to start going through insulation. Not good. So to get it back ready for where we are, near where you live, you will have a step down transformer, and that puts it down into our much lower thing for our homes and our factories. Okay, and obviously this is, as we know, and we need to remember, at 230 volts and at 50 hertz. Okay, obviously they can then ask you about ways that you're generating that. So disadvantages of fossil fuels, advantages of nuclear, disadvantages of nuclear, whatever. Okay, they love that for a long answer question. Okay. I haven't really done the resistance in a wire practical. I'll be honest, I think that's quite straightforward. Does anyone have any particular topics that they are desperate for now? I suppose we've done a bit of electricity. Some people are desperate for particles. I can do some radiation. I can do some energy. Whatever floats your boat. Should we do another poll? Oh, professional. Ask a question. Next top question mark. Particle model of matter. Or energy. Or essentially radiation. Or resistance in a wire. Okay, there's professional. Professional. Not scuffed. Why does my bottle start to go all kind of whistly all of a sudden? Okay. I'll give it another 30 seconds and provide a good snack break. 100%. Okay. Is there a particular thing in particle model of matter? Or just, I don't like particle model of matter? Oh, 50%. Oh my goodness. Because we're overwhelmed with people. Look, who says a vote doesn't matter? Oh, look, it was in front of me the whole time. Right. Okay. Okay. Right. So, particle model of matter. Right. It has a few bits to it. Okay. So, the first one is the kind of basics when you're coming to the particle model, which is what you've probably done all the way since year 7. Right, which is solid, liquid, and gas. Okay, remember solid, all nice and like that. Okay, gas all over the place. People trying to find that quite easy. The hard one is the liquid. Now, again, the mark scheme tends to say you have to have over 50% of them touching. So I like to kind of draw it almost like a solid, but I'll just kind of give them a jiggle because they can kind of move over one another. The first thing which I would say is properly GCSE with this is the concept of internal energy. Okay. Now you're probably used to saying low energy, medium energy, high energy. But what's actually going on? Internal energy is the sum of two things. It's the sum of kinetic energy, okay, plus the potential energy. Okay, and the kinetic energy is the movement energy, okay, and this is intimately related to the temperature, okay. So this is what gives us the temperature. Right, now here, they're only vibrating, so it's low kinetic energy, that's what it's called. Here, it's starting to move about a little bit more kinetic energy. Ooh, here, really whizzing about, lots of kinetic energy, hotter. Then we have this thing called potential energy, and this is all to do with the state, okay? Now, it's kind of like I've got two separate bank accounts. I can put money into one, I can put money into the other, okay? I don't really put both in at the same time, okay? And this leads us to the first kind of main thing, I suppose, and that is this graph. This is called a heating curve, cooling curve. It's going down, okay, where I've got the temperature, and over here I've got the time. Okay, now as I'm heating this up, okay, you would expect it to just kind of be a straight line, but that's not what happens. You get straight line, flat line, straight line, flat line, straight line. Why do you get this? Okay. In these sections here, okay, where the temperature's going up, that is the energy going into kinetic. Okay, so throughout the whole thing, the energy, if I did a graph of internal energy, it's going straight up. Okay, but this is not a graph of internal energy, this is a graph of temperature. On these flat bits, okay, on these flat bits, like here, the energy isn't going into making them move faster, it's going into the potential. Okay, it's splitting them up. Here, we're going from a solid to a liquid, and here you're going from a liquid to a gas. You're putting energy into breaking them apart and doing it like that. Okay, it's kind of like in a game where you get experience, right? And then eventually you need to like level up because it kind of caps you, right? So here you're putting in experience, right? I now need to spend time leveling up. Right, I'm now in a new level. I can put in more experience, put in more experience, put in more experience. Right, I now need to level it up. Right, I can now put in more experience, more experience, more experience. Okay, so throughout the whole thing, you'll kind of you're kind of increasing energy, but you have these flat bits. Now, what do they like to ask about you? They like to say, first of all, foundation level, it might be what is happening at these flat bits, change of state. If you've got an actual like cooling curve or heating curve, they might say like what is actually happening at each specific one. You could also ask you what is the melting point. Well, here is where I'm melting. I can look there, and that will be my melting point, and that will be my boiling point. Okay, so that's another thing that they might ask. Now, both of these kind of sections have equations related to them, and they're both in the equation sheet. So the flat bit, okay, where I'm changing state, okay, they are all to do with the specific latent heat equation. Okay, that's E equals M times L. And then these bits here, where I'm increasing the temperature, these are all to do with specific heat capacity. So the first thing you need to establish, if it's a question like this, is what is happening in the temperature. If it's going up, a specific heat capacity, staying the same, specific latent heat. So right, we'll come back to that because that's quite hard. We'll do it, but we'll do another one first. That foundation yeah, here we go. So this one, you can see I've got a change in temperature because it says the temperature of the air in the balloon decreased by 250. If I've got a change in temperature, that's a change in temperature. That means we're now looking at specific heat capacity. Okay. Now I know it gives it away here, but just bear that in mind. How many marks for grade 4? Are you combined or triple? So combined, about 50% is always a good show. The problem is with the equation sheet for physics, traditionally now the grade boundary has been a lot bit higher, so you're probably looking at about 45 marks now. You can just like that. By the way, the grade boundaries are all publicly accessible. Like you can literally type into Google AQA grade boundaries and search through that document, and you'll see them. You can do it paper by paper. So I think last year it was maybe 42, something like that. Yeah, of course it is. I mean, a 1-1's a pass. It's just people don't particularly like it. Yeah, like depends on what you want to do next year. But 4-3, not to be sniffed at. Okay, so here, and again from our equation sheet, we've got energy equals mass times specific heat capacity times temperature change. Now, why they decide to use theta? Because they're a bit edgy. Okay, it's just T in Greek. What's TH in Greek? But it's like 10th of the change. It's like Mike Tyson doing it. Yeah, it's all of them. That's the thing. Like people always are like het up on if it's foundation or higher and all this type of stuff. Like pretty much everything's in both. As if it's something which is specifically in higher, you know, then I'll tell you it's only in higher. Right. So again, from our equation sheet. That's our first thing. Always writing our formula. Then we go to insert. Let's stick our numbers in. Right. Well, we've got the air in the balloon had a mass of this. Okay. So M is now going to be 0.00320. Okay. Now, the specific heat capacity, I don't know, so I'm going to put that as C. Okay, the change in thermal energy of the balloon is was 806. Was 215. So that's 215. And because I'm a moron, here it should be 860. Okay, you would get a mark for that. Next thing, whoop, wobble, wobble, wobble. Next thing we do, okay, is, well, let's simplify this side. We now want to treat it like it's an algebra problem. So we've got 860 equals, stick that in the calculator, no such thing as a non-calculator science paper. What would that be? That would be, that might be a little bit tricky on the end. I did do some beautiful mental maths earlier. Been a long day, hasn't it? Yeah. 1.1 times 215 equals 0.688 times C. And again, now, oh yeah, so much maths. I think it's, it might even be more than 30%. So now I want to get C on its own. So let's divide both sides by this. 860 divided by 0.688 equals C. If they see that, or they see 860 divided by 0.0320 times 215, that's a mark. That's why we do our fixed step, because even if you muck up by seeing that, we're going to get our mark. We divide that through, okay, on our calculators. And again, 860 divided by 0.688 is 1,250 joules per kilogram degree C. So that is our answer. That's pretty hard. You'd get close if you smash all the maths. You'd get close. Right, let's do one on hard mode. So this is the type of thing you'd only really see in the higher, but you know, it's good lessons for us all in here. That's why I'm going to do it. Okay, it says the initial temperature of the mixture was +20. The mixture froze at -1.5. Okay, it says a total of 165 kilojoules of internal energy was transferred from the mixture to cool and freeze it. Right, so this is really tricky. So don't get yourself put off if you're like, no idea here. But this provides us a good opportunity to revise what we've just said. Remember we said internal energy is the energy from the kinetic plus the energy from the potential. So that means, right, that 165 kilojoules has gone to cooling it, okay, and that's all to do with specific heat capacity, and it's gone to freezing it, and that's all to do with specific latent heat, okay. So if I do both of those equations, okay, so the specific heat capacity is energy equals mass times specific heat capacity times temperature change. And here is energy equals mass times specific latent heat. Those two added together will be 165 kilojoules. So that's quite weird, because what you're saying is this thing plus this thing is going to equal 165,000. And that's your insight to then work through it. Now, I'm not going to spend the rest of the time doing it, because you know my class is foundation. I've got a lot of people here, but like, and I think most of you are foundation. But like that's our insight, and then it's just the same equation stuff as before. Right. Does anyone have any particular topic requests? I've kind of done particles now. I did electricity earlier a bit, so now really it's energy or the radiation stuff. I'll do a little bit of that. It's not going to be a long one tonight, so I'll probably do about 10-15 minutes more, unless people have particular questions. Energy, please. Okay, do you know the types of energy? That's the first thing to know. Okay, so way to remember the energy is kg cement. Okay, yeah, kinetic and stuff like that, right? So these are all the types of energy, and again, I always like to think about them as like money, right? You know how you've got like pounds and dollars and euros, right? These are our currencies of energy. We've got kinetic, they're called energy stores, gravitational potential, so that's the energy in being high up. We've got chemical, and the weird thing about chemical is it comes up in different forms. So that could be in fuels, because I can burn them. It could be in food, because that's basically our fuel. And quite a weird one is batteries. Okay, batteries and cells are stores of chemical energy. They are not stores of electrical. Electrical is not one of these stores. I can have elastic potential. I can have magnetic. I can have electrostatic, so that's in charged particles. I can have nuclear, and I can have thermal. Now, whilst these are all of the types of energy, overwhelmingly, that one's common, that one's common, that one's common, that one happens occasionally, and that one's common. You mainly deal with them. Okay. Now, the other thing which we need to know is how we transfer between them. And the way to remember the transfers is Mr. He. Okay, so Mr. He. And you can transfer by mechanical. So that's like physically moving something, physically touching. Yeah, I get you. I love a tip run. I love a tip run. I like going to the tip enough that when I see someone turning it in the wrong bin, I can tut at them. I'd say, oh, you don't want that there, mate. That goes in that one. Right, but yeah, the chemical goes in the other one, right? Because it's like stored up, but it's so easy to think of it as like electrical, but it's not, right? It's chemical, and then it goes via the electrical pathway to whatever you're using it for. So if I'm looking at a phone, right? So if I'm looking at the transfers in a phone, right? I have chemical in the battery, and then that will end up as, thermal, maybe. Okay, the phone gets hot. You have some of it going off via the radiation pathway. Okay, so that's light and stuff. Kinetic, it makes the speakers move and sound move. But this thing is happening via the electrical pathway. That is not a type of energy, it's a way of transferring electricity. So by going the chemical going via electrical to thermal. Okay. Now the cool thing about this is if you like to think about it like money, okay, what can you do with money? You can't print money, okay? So you can't create new money. You can't destroy money. The only thing you can do is change it. So, you can exchange your efforts for money. You can, if I've got £100, I can put it into dollars, I can put it into euros, I can change between them. Now, I know in real life, like, they take a cut of it and stuff like that, called commission, but let's pretend that like we're a lovely, perfect world, all right? So the thing that you can only do with energy is transfer it. Now, what that means is whatever energy I have before, right, it has to equal the energy after. That's such a fundamental idea, like probably the most fundamental idea in the whole of physics, like genuinely, and that's called conservation of energy. Okay, think of conservation like the word conserve means to keep the same, right? If I'm a conservative politician, I want to keep things the same back as they always were, right? If I work in animal conservation, I want to save them. I want to save the animals, make sure they're all nice and they're all the same. Okay, so conservation of energy means I want to keep it the same. Now, where does that rear its head? Well, it rears its head often with transfers. So we can talk about efficiency, right? So efficiency, again, it's an equation which is given to us. And efficiency is the useful energy divided by the total that you put in times by 100 to make it a percentage. So I don't know. Let's say I put 500 joules into a light bulb. Look at that. I know what you're thinking. Are you doing art GCSE? Well, it's not obvious. 500 joules on that. Let's say 50 of that goes as light that you like. Okay, and 450 is thermal. So let's think about this. What is the useful energy? Okay, well the useful energy is the light that you want at the top. That's 50. The total energy is 500. That's what's going in. Okay, times by 100, that would be 10%. Okay. Hello. Do you have any particular questions? Because I'm rambling here until people give questions. Well, you're going to be about 10, 15 minutes more. So that's 10%. I did the electricity earlier, unfortunately. I'm sure you can scroll back on the live stream and see. You could try and pinpoint exactly where I lose my mind. Some of you might say I never had it. But I did a bit of electricity earlier. Yeah, that's 10%. Now, good thing here, and this is what I say always to people, is have a sanity check. Okay, so about 10 minutes before the end, imagine that I storm into the exam hall and I go, right, sanity check. And what that means that you want to do is check, have you done the tick boxes? Have you done the fill in the gaps? And the other thing you want to do, especially here on the maths one, is does your answer make sense? Now, this is efficiency. Now, efficiency cannot be below 0 and it cannot be above 100%. Okay, it's like a probability. I don't think you are clueless. I think you're probably less clueless than you think. I would say, as long as you get happy with FIFA, right, or however you have been taught, but I would suggest FIFA, doing equation questions, you will get an all right mark. Okay, I'm not saying you're going to light the world on fire, but if you can do the equation questions, that's a skill. That's not something that you need to worry necessarily about revising, because it's a skill, right? It's not a bit of knowledge that you need to remember off your heart. So yeah, a good sanity check here would be like, have I done an efficiency and it ends up being over 1 or over 100%? It's like probability. That would be silly. I remember there was a question a few years ago where if you didn't change the units, it was like, how high would the toast pop out of a toaster? And I had people put 1,000 kilometers as the answer, right? But if you did a sanity check, you'd be, well, obviously, I'm not putting the thing down on a toaster and the toaster's being launched into space, right? It's obviously going to be like, you know what a toaster is. So that's what I mean with like a sanity check. Right, I tell you what. Rambled a little bit about energy. Let's do a couple of energy stuff. Or let's do radiation. We've done any radiation, and I feel like we've talked about radiation. Okay. Right, before I ramble on that, okay, there's actually 3 types of radiation, okay, that you need to worry about. 3 types of ionizing radiation, and that is alpha, beta, and gamma. Okay. Oh, he's on fire. Right, now, all of these are the idea of I have an unstable nucleus and it wants to get stable. Now, just like some of you right now, you're feeling a little bit vulnerable, feeling a little bit thing. How do you start to feel a bit better? You have a breakdown. Okay? Now, it turns out that when atoms break down, they're all ionizing. Yeah, they're all ionizing. When they have a breakdown, atoms can do it in 3 ways. They can do it in the way that we call alpha, the way that we call beta, and the way that we call gamma. This is just A, B, C in Greek because scientists like to pretend that they're really clever. Okay? That's all it is. It's literally A, B, C. All right, now alpha, okay, is where it breaks down by losing a lump, which is 2 protons and 2 neutrons. Okay, so this is made of 2 protons and 2 neutrons. Now, because of that, it's often called a helium nucleus. Okay. All right. Now, beta is where we lose a little electron. And it's not from the outside where we think electrons are. It's an electron, but it's weird. It comes from the nucleus, right? It's an electron from the nucleus. It's like a fast electron. And then gamma. I know it's in paper too, so you don't have to worry about it. But you know when you do waves and you do radio waves, microwaves, infrared, radiation, all of that fun, right? That is the same thing there. That's an electromagnetic wave. It's a high energy electromagnetic wave. Now, here's how I like to think about them. Please do not write this in the exam. I always think about alpha as like a sumo wrestler. I think of beta as like a year 7. And I think of gamma as like a ghost. Right? Now, this is a big, big old lump. 2 protons, 2 neutrons is heavy. Okay, its mass is 4. Big, huge. All right? Now, just like a sumo wrestler, if they run into you, that's going to cause a lot of damage. Now, we call that its ionization power, right? Because we're measuring how much it will knock electrons off atoms and turn them into ions. And the ionization power of alpha is really high. Because if I ran into a sumo wrestler, he's going to send me flying. Okay? Now, how far does it go? This is where we come to something called penetration power. Now, if I was being attacked by a sumo wrestler, it's actually quite easy to get away from. You just jog slightly in the other direction. He runs out of breath. Easy. Okay? So, if he hits you, big damage. Right? But it's easy to get away. Now, it's the same thing with alpha radiation. If the alpha radiation is, say, inside you, it's going to cause loads of damage, right? If it's in a gas and you breathe it in, right, it's an alpha source, starts making alpha radiation, problem, okay? But it's actually easily stopped. It's stopped by paper. It's stopped by only a few centimeters of air. And that's actually why we use alpha in like smoke alarms, or we used to, because it would get stopped by the smoke and it would trigger the smoke alarm. Now, I said beta. Let's imagine it's like a little year 7. Now, their mass is actually very small. It's about 1 divided by 1,800, just like a little small year 7. They're nippy. They're wily. Okay, they start thinking they're rebels. They'll run the wrong way, done a one-way system, right? All of this stuff, right? And maybe, you know, if a supply teacher comes out or something, okay, they'll ignore him because they think they're mad lads, right? Now run through, okay. If they hit into you, they're annoying, right? They're not going to cause big damage like sumo, okay, but they're going to cause like a medium amount of damage, all right? But the penetration power is, again, we can think of it as kind of medium. This, we need something a little bit more solid to kind of stop them getting away. And that we tend to typically say aluminium. Okay? And then finally, gamma. Gamma, right? It's like a ghost. Its mass is literally 0. Okay? Now, gamma, its ionization power is actually quite low. Right? Because if a ghost moves through you, you go like, oh, right? You go, oh, what's going on there? Not that ghosts exist, but that's a debate for another time. But they'll go through everything. Their penetration power is really high. To stop them, we need something like a thick lead. Okay? So we kind of got this trade-off. If you imagine that you've got high ionization and low penetration for the alpha particle, and then it kind of flips, all right? So we've got alpha, beta, and gamma. Now, at foundation level, they straight up like to ask about the stats, right? What one's got the highest penetration power? That's gamma. Okay. What one has is stopped by aluminium? Beta. Okay. See if I've got a good one. Yeah, so look at this. What a question, right? What a long answer question. It says explain the differences in properties of alpha, beta, and gamma radiation. So let's explain. So that means you need to say why. Okay. Right, so it's not just like what is going on. It's not describe. Okay, it's saying why. Okay, and remember, you can answer in bullet points. Okay, so let's think about alpha. Okay, what is it that we know about alpha? Okay, alpha, the properties of it, okay, is it has high ionization power. Why is that? Okay, because it's a heavy particle. Okay, it has low penetration power. Again, that's because it's a heavy particle. Okay, you could say it's deflected by electric field. And it's quite weird. That's because it's that is 2+, right? So it's got a charge. That's because it has a charge. Okay, and what beta like? Well, beta is a medium. Okay, so you could say even say like this is because it's a helium nucleus, right? Beta has got a medium ionization power. Okay, it's stopped by aluminium. Okay, why is that the case? This is because it is a fast moving electron. You're linking it back to what it is. They are all ionizing, absolutely. Yeah, just to different levels. Okay. But because it talks about differences, that's why I'm kind of not going to say they're all ionizing, because that would imply similarity. Okay, we're just focusing on difference. And then I've got gamma. Okay, well, gamma, okay, has got low ionizing power. Okay, it needs thick lead to stop. So I'm answering this like I'm like running out of time at the end of the paper, right? Okay, why is that? Okay, it's because it's a high energy electromagnetic wave, right? And I scrambled an answer there in the last 2 minutes. Okay, and I'm home for tea and cake. Right, another little kind of idea just to think about here is these nuclear equations. And the thing about nuclear equations is, and my advice is to imagine that there's like a little equal sign there. There's like a little invisible equal sign. Okay, and whatever I have on the left, I've got to have on the right, just like I would in an equation. All right, so if I've got 89 here, that means A plus whatever number is there, okay, it's got to equal 89. Okay, so let me do a different one just as an example, right? So let's say I've got uranium 238. Okay, now this actually does alpha decay, and given what we've said before here, alpha is 2 protons, 2 neutrons, like a helium nucleus. So I'm going to do a little alpha symbol, and it would have a top number of 4 and a bottom number of 2. So given what I've said, whatever I have at the top, I have there. So 238 equals something plus 4. Well, that's going to be 234, because 234 plus 4 is 238. And again, down here, something plus 2 is equal to 92. That's going to be 90. And again, you're not expected to be able to find it on the periodic table, but you would see that that's 4 in TH. So if I look over here, beta, it turns out, the stats of the particle is 0 on top and -1. So 89 equals something plus 0. Well, that has got to be 89, right? Because it's got to be the same. Plus 0 means that's 89. This is beta is the hardest one for these equations. And you can see here why. Because people will easily go, I take that -1 and that'll be that. But 38 equals whatever number that is, -1. That actually means that that's got to be 39, because 39 minus 1 is 38. So that would be 39. That's quite tough. Right, the last thing I'll do before I head off, okay, is there was a half-life question. Okay. Now, the other one is contamination versus radiation. Contamination is the unwanted presence of the material. So that means it is physically on you. And radiation is simply you're being exposed to it. So in this question, it says radioactive dust from the nuclear weapons testing settled on the desert. So that means it's physically on the desert, and that means it's contamination. Okay, if I was stood there watching a nuclear bomb go off, right, and I got the radiation kind of hit me in the face, that means that I would have been irradiated. If I then start breathing in all the radioactive dust, that's contamination. Okay. Now we then get this thing called half-life. Okay. Now half-life is basically the time it takes to halve. Right, be that activity, be that number of atoms. So can you see here, the activity is 80. So to halve, it would have to get to 40. And if I read across to 40, and I read down here, that would give me 12.5 years as our half-life. Now, in another 12.5 years, okay, it will have halved again. So after 25 years, it will be at 20. Okay, and after another 12.5 years, it'd be at 10. And after another 12.5 years, it'd be at 5. So it's permanently this halving business. Okay, so you can see here on foundation, they tend to hold your hand through it, right? How much time did it take for the activity of the sample to decrease from 8 to 40? That's 12.5 years. You can see it from my thing. Now, here's your last kind of question spot thing. If you have something like this where there's no line of working out, the answer can be two things. It's either same as above or it's 0. Now, given the fact we've gone from 8 to 40, that suggests that it's got to be the same as above, which is 12.5 years. Okay, or because I've written it in that thing in my flusterness, I've gone 12.5 years. Cool. We'll call that ramble over. Does anybody have any final questions before I bid you adieu? So I appreciate it's been a bit rambly. Anyone have any final questions? It's nice to get peak viewership just on about a go, isn't it? Right. Hopefully that was useful in any way, shape, or form. It was a bit of an annoying start with my computer crashing and stuff. And you know, I think I'm a bit tired myself. Just relax into it. Remember to follow FIFA. Do your equations to the best of your ability, and I'm sure it'll be okay. Okay, you're getting there. 2 weeks left. That's it, and you're all done. And you have the best summer ever. Okay, right. Thank you very much, and have good luck. And have a lovely rest of your evening.